So 7.1b is called sampling variability. Okay. So how can X bar, that's the mean of a sample, based on a sample of only a few thousand of the 121 million American households, be an accurate estimate of mu, which is the true mean? Okay. After all, a second random sample taken at the same time would choose different households and likely produce a different value of X bar. This basic fact is called sampling variability. So the value of a statistic varies in repeated sampling. So you should write that definition down. So sampling variability, the value of a statistic varies in repeated random sampling. So we got like $69,677 for I think we were doing the mean income. So if you took a different set of data, you might get a different mean income. All right, so to make sense of sampling variability, we ask, what would happen if we took many, many samples? And here's how to answer that question. Take a large number of samples from the same population. Okay, so we're going to take a group of, whatever, 10 houses, another group of 10 houses, another group of 10 houses, or maybe it's 50, and another group of 50. Calculate the statistic, like the sample mean or sample proportion for each sample. And then we're going to make a graph of the values of the statistic. Okay, so we're going to take a ton of samples and make a graph. Examine the distribution displayed in the graph for shape, center, and spread. What is this, you guys? Yep. You're going to do socks, as well as outliers or unusual features. All right, so you're going to take a bunch of samples and then describe the distribution, which is shape, outliers, center, and spread. Okay, we're not going to actually do this. We're just going to pretend to do it. All right, so otherwise this will take forever. So you've got 200 colored chips in a bag, and 100 are, say, red, and then another 100 are, I don't know, black, whatever the other color is. Okay. So some red, I think some are blue actually. So it's supposed to be 50-50, so we're talking proportions. So P, the true proportion, is 50%. So P without the hat is the true proportion. But we're going to go around the room, and you guys would each draw 20 chips from the bag. And the whole bag's the population. There's 200 chips. But then each person is drawing 20 chips. And you're going to write down the proportion of red chips that you got. Okay? So maybe you got 13 out of 20. Maybe you got 9 out of 20. Maybe you got 5 out of 20 that were red. And everybody would go through and do this like twice. All right? So P is the true proportion of 50%. And what you're finding is a bunch of P hats. Okay? So again, maybe you got 11 out of 20, whatever percentage that is. Another person gets 8 out of 20. Okay? And then we convert it to a decimal, and we make a dot plot of everybody's dot on what P hat they got. Okay? So here's an example of somebody's dot plot. So here's our true proportion at 50%. Some people did get 50%, right? They got 10 out of 20 when they drew out of the bag. But some people got 70% that were red. Some people got 20% that were red. All right, so we took a bunch of samples and we look at the socks. Anybody want to raise their hand and tell me what the shape is of this distribution? You guys remember how to do this? Shape. Vaughn, what do you think? You could say left, maybe a little bit left skewed with this guy pulling it left, right? But I would probably say roughly symmetric, okay? But that's okay. All right, so there's our shape. The graph is roughly symmetric with a single peak at 0.5. All right, outliers. Lucas, what do you think? Any outliers? Okay, this might be an outlier. You could say that. And let's go center. Sam, what do you think for center? Okay, I agree. 0.5. And then we've got the spread. So far, all we've learned is range, right? The range is from 0.2 to 0.7. However, we're going to learn a new formula. You might want to write this down. Sigma p hat. This is the standard deviation of all the p hats, so all the sample proportions. And it is the square root of p times 1 minus p divided by n. Where p is the proportion of reds, if we know the true p, we can plug it in. So in this case, it would be 0.5 because we're talking about proportion of reds. And then it'd be 1 minus 0.5 divided by n. N is the number in the sample. In this problem, we've got that they drew 20 chips, and so n is 20. All right? And you get a lovely decimal, something like 0.122. So that's how they did spread, is they actually calculated the standard deviation. We're going to do a lot more on that. This is just kind of an intro. All right? So they wrote there's no obvious outliers. If you said 0.2 is potentially an outlier, that's fine. They also got an exact mean right here by actually calculating it, but you can also estimate by looking at the graph. So, of course, the class only took 36 different simple random samples of 20 chips each. So they had 36 students, or maybe they had 18, everybody went twice, right? But they took 36 samples, 20 chips each. There are many, many possible simple random samples of size 20 from a population of size 200. In other words, how many different ways can I draw 20 chips from a bag of 200? Well, about 1.6 times 10 to the 27th, actually. That's lovely. So if we took every single one of those possible samples and calculated the value for each, and then we graphed them all, we'd have what's called sampling distribution. So write this definition down. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. In other words, we got a bag of 200 chips. How many different ways can I draw 20? That would give us the sampling distribution. Not really possible to do, right? That would take forever to take that many samples. But the more samples you take, the better your data. All right, so let's try a problem. So this is simulating a sampling distribution where we get a whole bunch of samples, okay? So we use Fathom software to simulate choosing 500 simple random samples of size n equals 20. So instead of 36 samples in the class, now we're doing 500 samples. We're still drawing out of that bag of 200 only 20 chips and calculating the proportion of reds, okay? So part A, there is one dot on the graph at 0.15. Explain what this dot means. So here's this tiny little dot, and we have a p hat of 0.15. Anybody know what that means? What does that one dot represent? Thanks. He is not here. Anyone have a guess? What does every dot represent, you guys? One sample, right? How many chips did we draw in a sample? 20. So this would be the same as 15 out of 100, but we need to convert this to out of 20. This counts as one simple random sample of 20 chips, and if we converted this, that would be 3 out of 20 that we got as red. So one person drew 20 chips. They got 3 out of that were red. That's the same as 0.15, and you plot your dot on the dot chart. Okay, it's one simple random sample of 20. All right, so each of these represents that proportion that somebody got. All right, B, describe the distribution. Are there any obvious outliers? Same thing we just did, guys. If it says describe the distribution, what do? Socks. I'm not going to do it again. It's really similar to the last one, right? Would it be surprising to get a sample proportion of 0.85 or higher in a simple random sample of size 20 when the true P is 0.5? This is really important, and we started doing this kind of last year, the end of the year, or semester, okay? Our true P is 0.5. We know that, right? We know the bag has 100 red, 100 blue. How weird is it to get 0.85 or higher? Did we ever get, I know it's hard to read, this is 0.8 right here. Did we get ever 0.85 or higher red chips when we did a simple random sample and we did it 500 times? Nope, we never got it. So it's very unlikely that that would occur. It says to justify your answer. How would you justify that? Well, we took 500 samples and we never got a proportion higher than 0.85. Okay? That's how you justify that. Suppose your teacher prepares a bag with 200 chips and claims that half of them are red. A classmate takes a simple random sample of 20 chips and 17 of them are red. What would you conclude about your teacher's claim? So again, now let's say we do get that weird number. We got 17 out of 20, which is what percent, you guys? 85. All right. So if we do get that, could you question your teacher's claim? Yes, you could question their claim. There may not be exactly 50-50 red and blue. Make sense, guys? All right. This is important that you want to write down. Something about each of these graphs. So population distribution, you want to know what the heck that means. Distribution of sample data, and approximate sampling distribution. So there's 3 things. So the first one, write down population distribution. This is the distribution of what's actually in the population. So they drew a little bar graph, and we had 100 that were blue and 100 that were red. We could have also done this with percents and had 50% blue, 50% red. All right, so that is called the population distribution. It is a bar graph. You might make note of that. And it represents the population, okay? And then we have what's called the distribution of sample data. You have to think of this as one draw, like when we're drawing out of the bag, or one sample. That might be a better way to write it. This represents only one sample. So maybe I drew out of the bag, and I got 8 out of 20 that were red. So we have a little bar graph. 8 are red, 12 are blue. Here's another distribution of sample data. Somebody drew 13, I think that says. Can't read. Come back here. 11, just kidding. 11 red, and then 9 are blue. So notice each of those represents one sample. Again, this is called a distribution of sample data. And then we have this one that's important called a sampling distribution. They sound really similar, right? You have to know the difference. A sampling distribution is a whole bunch of samples, and we make a dot plot, right? So we've got a dot plot, and we've got many samples. It's no longer a bar graph. They all changed to little p hats, and we have a whole bunch of p hats in there, okay? So the population distribution gives the values of the variable for all individuals in the population. That's what we talked about. And the distribution of sample data shows the values of the variable color for individuals in the sample, in other words, for one sample each. And then the last one is called sampling distribution, and it's the whole entire thing with a whole bunch of samples. Okay? So let's see if we can tell the difference. Yeah, we got that. All right, so Mars Incorporated says that the mix of colors in its M&M's milk chocolate candies is 24% blue, 20% orange, 16% green, 14% yellow, 13% red, and 13% brown. Assume that the company's claim is true. We want to examine the proportion of orange M&Ms in repeated random samples of 50 candies. Graph the population distribution. Did they tell us how many M&Ms exist in the world? No, they did not. So you cannot do it by frequency. What do you have to do it by? Percents. So it's just a population graph, a bar graph, and we're going to do it by percents. Okay, because we don't have a certain number, so you just list them out. On the side you have percents, and there's a lovely graph of the population data. All right, so population distribution is what that guy looks like. Now it says, imagine taking an SRS. That means one simple random sample of 50 M&Ms. All right, so you drew 50 M&Ms, make a graph showing a possible distribution of the sample data. It doesn't have to be exact, but you could multiply your percents times 50, right? And we can get frequency on this one. Again, this is one draw of 50. So they picked that there was like 9 blues, and there was 11 oranges, and 12 greens, right? What should this add to? Right? There's 50 total M&Ms here. It doesn't have to be exact. You get to imagine it, right? So you just get to pretend like you drew, some different M&Ms. Notice this represents one sample. All right, and what is this called again? Yep. Okay, distribution of sample data. And this last one says, which of the graphs that follow could be the approximate sampling distribution of the statistic? So now we've got this vocab word, sampling distribution of the statistic. That's a whole bunch of samples. So it's definitely not this one, right? It's a whole bunch of samples. And what were we actually talking about at the beginning of this problem? The proportion of oranges, which is supposed to be 20%, right? So if I take a whole bunch of samples, it should still be 20%. I can't read this one. Someone in the front, what is that? That's 40. This is 20. Which one's correct? The one that has 20 in the middle, all right? The more p-hats you take, the more accurate it should be to the true proportion of oranges in the bag. Grace?
So, what if it's like we're trying to find the that's just their guess?
That's fine.
What if they're truly wrong?
Oh, yeah. So this is probably the answer. When you start getting to stuff like you actually take this many, then you can make, you can say there's evidence that there's really more than 20% in the bag. Yeah. For now, pick the one that matches. Okay. And that is it, you guys. 7 through 12.